Let's first start off with a little warm-up reviewing yesterday's material. It says use the graph of f of x to find the y-intercept in zeros, then find these values algebraically. So it's a multiple choice test, and in this case we can kind of rule out a couple answers right away. If you notice that, number one, the y-intercept looks to be slightly above the value of 8, so between 8 and 10, so I'm assuming the y-intercept is going to be 9. So we can sort of rule out the choices of B and D especially because of the fact that the 0 said it's a -1. And remember, a 0 is where it crosses the x-axis, and if you look at this graph, notice that the two zeros here are both positive, so it can't be D also. So now we need to use algebraic methods to figure out whether it's A or C, because in both cases it has a y-intercept of 9. It looks to us that the choice of C would be our only correct answer. So if we use our algebraic methods to determine really the zeros, remember the zeros is where it crosses the x-axis. This is where the y-coordinate is 0. So if we set this function equal to 0 and solve for x, we should be able to find these zeros algebraically. This is a quadratic function. There are many methods to solving quadratic functions. One of the easier ones is to actually factor this out and determine what the zeros are. So in this case, notice that there is a coefficient of 2 in front. And if you dust back your cobwebs from FST or Accelerated Algebra 2 last year, we multiply that to the backhand side. This is called the voodoo method. And it becomes x squared minus 9x plus 18. We factor this like any typical problem, so we look for factors of 18 that add up to -9. I'm thinking both have to be negative because the middle term's negative. So I think it's -3 and -6. And again, you can check by foiling it out to determine if you're correct. Now, the reason it's called the voodoo method is because that number that we dropped initially, that 2, this is when we introduce it back in the mix. We divide each of those numbers in each factor by that value of 2. And we simplify. So notice 3 over 2 doesn't simplify, but 6 over 2 becomes 3. So our final answer in fully factored form would be x minus 3 halves times x minus 3 equals 0. Now to find the zeros of this function, we have to ask ourselves what makes this 0. So if you notice, if we plug in a value of +3 here, that would make the whole function 0. So x equals 3 is one answer. And if I plug in a value of +3 halves here, it also becomes 0. So x equals 3 halves would be your other 0. So if you look back on our choice, today we are going to continue on lesson 1.2. And the objectives today are determine if a relation is symmetric with respect to the y-axis, x-axis, or origin, and by using the graph and algebraic methods. Determine if a function is even, odd, or neither. So let's first talk about symmetry. In pre-calculus, we talk really about two types of symmetry. One that's called line symmetry, and the other one called point symmetry. The definition of line symmetry is a graph that can be folded along a line so that the two halves match up exactly. One good example of this is the basic x-squared graph, your parabola. If you notice, if you imagine our y-axis being the line that you would fold along this graph, and if you were to fold that up, the two halves of the parabola would match up exactly. Point symmetry is a graph that can be rotated 180 degrees around some kind of point. And when you do that, it appears to be the exact same graph as the original. An example of this is your basic y equals x cubed function. If you graph the y equals x cubed function, you get a graph that looks like something like this. Now if you rotate this thing 180 degrees in either direction, it's actually going to match up to the exact original function of y equals x cubed. There are really three types of symmetry we look for in pre-calculus. Functions that are symmetric about the x-axis, y-axis, and symmetric about the origin. There are three examples that we can look at. Taking a look at the x-axis, the graph of a relation is symmetric with respect to the x-axis if and only if, for every point xy on the graph, the point x comma negative y is also on the graph. So an easy way to test this is to replace your y with negative y and to see if it produces the same exact equation. If we take a look at the y-axis, it says the graph of a relation is symmetric with respect to the y-axis if and only if for every point x comma y on the graph, the point negative x comma y is also on the graph. So an easy algebraic test for this is to replace x with negative x and to see if it again produces the same exact equation back. We'll take a look at a couple examples after this slide. And lastly, with the origin, it says the graph of a relation is symmetric with respect to the origin if and only if for every point x comma y, the point negative x and negative y are also on the graph. So again, the algebraic test is to replace x with negative x and replace y with negative y. And when you do that and substitute that into your equation, the result is the same exact equation from before. It would be symmetric about the origin. You can pause this video at any time to take notes on some of these examples. Let's take a look at this first example. It says use the graph and equation y equals x squared plus 2 to test for symmetry with respect to the x-axis, y-axis, and the origin. Support your answer numerically, then confirm algebraically. So if you even just take a look at the graph, it looks to us that it's definitely going to be symmetric about the y-axis. So for example, if I draw a line here, in this case is a good example of line symmetry. If I draw a line right on the y-axis, if you were to fold those two branches of the parabola up, they're going to match up equally. But we need to prove this algebraically, like it says. So if you take a look at this example, and let's go through each case. Now remember, the x-axis says that if we replace our y value with a negative y value, and that we get the same exact equation back, then it's going to be symmetric about the x-axis. So let's try it out. So I'm starting with our y equals x squared plus 2 function. And if I replace the y value with negative y and solve for y, so to solve for y I'd have to divide that negative out to each term on the other side. Notice that we get y equals negative x squared minus 2, which if you look at and compare to the original, it is not the exact same. So we know for a fact that this is not symmetric about the x-axis. Let's check the y-axis. So if you look at the y-axis, remember in the case here, we change every point, we change the x value of being opposite and to sub that in. So if we start with our original equation, y equals x squared plus 2, and replace x with negative x, so it becomes y equals negative x squared plus 2, and simplify, notice that in this case we have the exact same equation as the one before. They are the same. So in this case this confirms that it's symmetric about the y-axis. Now just for the last sake as a test, if you look at the origin, remember in this case that means we replace x with negative x and we also replace y with negative y, and to see if we get the same equation back. If we don't, it's not symmetric about the origin. So let's check. We get y equals x squared as our first original equation. If I combine these and replace y with negative y and replace x with negative x and simplify, so remember when you're squaring a negative it still becomes positive x squared here, and dividing that negative over, you'll actually get the same answer as x-axis equation, which was not the exact same as the original, so therefore again this one is a big no. So y equals x squared plus 2, we can say, is symmetric about the y-axis, and we confirm that algebraically. Let's take a look at another example. It says use the graph of the equation xy equals negative 6 to test for symmetry with respect to the x-axis, y-axis, and origin. Support it numerically and confirm algebraically, so just like before. So remember that testing for symmetry about the x-axis, we need to replace y with negative y to see if we get the same exact equation. So in this case, our original equation of xy equals negative 6, we can replace the y with negative y. And notice right away you get negative xy equals negative 6, which is not the exact same as the original. So in this case we'd say that it is not symmetric about the x-axis. Let's check y-axis. Remember, with y-axis we replace x with negative x and keep our y-coordinate the same. So in our equation form, we start off with xy equals negative 6, which is our original equation. If I replace x with negative x and simplify, we get negative xy equals negative 6, which is again not the same as the original. So in this case, we'd say it's not symmetric about the x-axis either. So lastly, the origin. The origin combines the two. We'll replace x with negative x and replace y with negative y. And again, to see if it's the same equation back. In this case, if I replace, so we start off with our original equation. If I replace x with negative x and y with negative y, notice when I simplify, negative x times negative y becomes positive xy, which is the exact same as the original equation. So we can confirm that using algebraic methods, we've confirmed that this function is symmetric about the origin in this case, because it's the only one that's the same as the original equation. Two last things today. We need to talk about even and odd functions. What an even function is are functions that have symmetry with respect to the x-axis. So in our examples before that we found functions to be symmetric about the x-axis, we can actually classify these as even functions. The test for this is that simply we sub in negative x wherever we see x for our function, and when we simplify and our output is the exact same function back as the original, we can classify that as an even function. Now for odd functions, these are functions that have point symmetry with respect to the origin. The test is the same as an even function, but in this case when we sub in negative x in for x and we see that we have the exact opposite of the original equation, the original function, then we know that our function is symmetric about the origin and we can classify it as an odd function. So let's take a look at a couple examples of determining whether functions are even, odd, or neither. In this example it says, is the function f of x equals x squared minus 4 even, odd, or neither? Now you don't have to check all three. In fact, if you notice on the previous slide, the big test was that if we sub in negative x in for x, if we get the exact same equation back, then we know it's even. If we sub in negative x in for x and get the exact opposite of the function back, we know that it's odd. And if you don't get neither the same function or the exact opposite of the function back, then we say it's neither. So let's just use this test to determine what it is. If I sub in negative x in for my function, it becomes negative x squared. You're replacing x with negative x, and we still have that minus 4 on the outside. If we simplify, negative x squared actually becomes positive x squared, and again we still have that minus 4. Look at your equations and compare. Are they the same? Are they the exact opposite? Or are they neither? Notice in this case they are the exact same as the equation before. So in this case we can classify it as an even function. And lastly it says describe the symmetry of the graph of the function. Well, if we know it's an even function from before, that means it's symmetric about the y-axis. Let's take a look at another one. So in this case we have a different function. F of x equals x squared minus 4x plus 4, and we still want to determine whether it's even, odd, or neither. So again, remember the test. The test is the same for even, odd, or neither. We sub in negative x in for x and to see what we get. So let's do that in this case. F of negative x would then be, if we replace negative x with x, or replace x with negative x, it becomes negative x squared minus 4 times negative x plus 4. Simplify as much as possible. If we simplify negative x squared, it still becomes positive x squared, because negative x times negative x would be positive x squared. But negative 4 times negative x becomes positive 4x, and we still have the plus 4 on the outside. Compare this equation with the original. Is it the exact same? I don't think so. Is it the exact opposite? If it was the exact opposite, you would see f of negative x being negative x squared plus 4x minus 4. If it's the exact opposite, then that means each term has to have the opposite sign of the original equation. And in this case, it's not. So our answer here is actually neither. And when it's neither, we can't describe the symmetry of the graph. Let's take a look at our last example today. It's a multiple choice question. Is it even, odd, or neither? Well, here we have a function y equals negative x cubed. So let's test. Let's test whether it's even, odd, or neither. An odd function, which in this case would be symmetric with respect to the origin. Now remember, the test is the same for all three. All we have to do is sub in negative x in for x and determine whether it's the same, the exact opposite, or neither. Our original equation was y equals negative x cubed. In function notation, that's f of x equals negative x cubed. So let's replace x with negative x to determine whether it's even, odd, or neither. So in this case, it would be negative, and I'd replace x with negative x and simplify. Well, remember, any odd powers and negative values, our output's going to be negative x cubed here. So in this case, we have, if we simplify, we still have the negative on the outside. And if you simplify negative x cubed, which is actually negative x times negative x times negative x, negative times a negative times negative is a negative, and x times x times x becomes x cubed. So actually we get negative x cubed inside. And if we take, well, a negative times a negative, it becomes a positive. So our end result is positive x cubed, which notice is not the exact same as the original, but in this case it's the exact opposite. So we would classify this as, here is your homework. You can get started on tonight. Don't forget about, take advantage of the Canvas discussion page. I'll try to check that frequently. Tomorrow we're going to review all this material so that you guys are well prepared for Thursday's quiz. Have a great rest of your day, and we'll see you tomorrow.